Guys, today we got mathematical induction. You need to really pay attention to this video. If you're one of these people who just kind of casually watches or whatever, you need to really watch. There's 4 slides after this. It's not gonna be a long video, but you really need to get this the best you can to have some success tomorrow in class. I don't say that very often, but this is one of those. So please, please, please take it seriously. Okay, mathematical induction is a special kind of proof. Okay, that's usually a bad word coming out of geometry. You did proofs in geometry. These are called inductive proofs today. It's stuff like this. Like, look what happens when you add consecutive odd numbers beginning at 1. Look at the sums you get. You get 1, 4, 9, 16, 25. Those are all perfect squares. So the key is, can we prove that happens forever, or is it just something that happened on the first 5 or 6? So that's what we're going to do. We're going to prove something inductively, because we can't go through every single number for the entire, to infinity to see if it lasts forever. So we're going to do what's called inductive proof. Here's how they work. We're going to do 2 steps. I'm not going to read all this to you, but 2 conditions must be satisfied. You got to prove it's true for P of 1. You got to be able to plug in 1 and show that it's true. And then you got to show that it's true for the K plus 1 term, the next term. If you can show that's true and the next term is true, then we're going to say inductively that it's true for all natural numbers, no matter what you plug in. Okay, so I'm going to show you 2 examples. You need to really watch these 2 examples. I mean, I keep saying that, but you need to. This is brand new stuff for you. Please, 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 again, watch these carefully. 2 examples. First one is what we just saw. We're going to prove that if you add up odd numbers beginning at 1, you're going to get a perfect square every time. Okay, so the first thing you do is you see if it works with 1. So I'm going to take the first term up here is 1. Does that equal, take the right-hand side, does that equal 1 squared? And it does. So we put a check mark. We've satisfied the first step. That's easy. That's the easy part. Okay. Second part is we got to prove that it's true for the next term. Well, the next term after 2n minus 1, matter of fact, the 2n minus 1 is the pattern for odd numbers, by the way. If you put a number in for n right there, no matter what you put in, it's going to be odd. That's the next odd number. So the next term after 2n minus 1, watch this, would be 2. I'm just going to replace the n with an n plus 1. Like that, minus 1. There you go. That's the next term. Now, because I added that term to the left-hand side, I'm going to have to add that term to the right-hand side to keep it equal. So I'm going to, the term I just added, the 2 with the parentheses, n plus 1, minus 1. Add that to both sides. I can't close it. I'm out of room on my iPad to close that parentheses. Now, here's how you know if it works. We started here with n squared. Okay, that's what the sum is every time. It was however many odd numbers there were, you just square it. All right, now, if this works for the next term, instead of n squared, I should get n plus 1 squared. That's what I'm trying to get. I'm trying to get the n plus 1 to replace the n, and that's going to be true in every problem that we do. So all I'm going to do is, all I'm working with is the right-hand side. I've got to somehow make that right-hand side be n plus 1 squared. And I know that before I start. It's got to be the next term. It's got to be true for the next term. Okay, so I'm going to take what I wrote over here and just work with it. Okay, so I'm going to start with this parentheses. I'm going to distribute the 2, and I still have that minus 1 out there. Okay, which gives me this. It gives me n squared plus 2n, and I have the 2 minus 1, which is 1. Now, think about factoring that. If I factor that, it'd be n plus 1, because 1 times 1 is 1, and 1 plus 1 is 2. So that's n plus 1 squared. You know what? That's what I needed. Check. Okay, so what we did, again, we proved it's true for the first term, and then we went the next term after that, and it has to equal the next term after n squared, which is n plus 1 squared. We proved that. I hope that makes a little bit of sense. Let me show you one more. Okay, now we're proving that for every natural number, if we add just 1, 2, 3, just straight up ends, the sum is always this. So what we're going to do first, again, you got to check the first term. So does 1 equal, and I'm going to plug 1s in over here. Does it equal 1 times 1 plus 1 over 2? Just plugged in 1s. That's going to give me on the top 1 times 2 over 2. Guys, that's 1. Okay, so that works. Now, that usually is going to work. So now I'm going to take this side over here, and I got to make sure it works for the next term. So I have n, the next term after n is always going to be n plus 1. Okay, that's the next term. So what I'm going to do is I'm going to take this right-hand side and add the same thing to the right-hand side that I added to the left, which is the n plus 1. Okay, now, again, all I'm going to worry about is this right-hand side. What do I want it to equal? I want that n right there to be n plus 1. I want that n right there to be n plus 1. You got to replace the n's with the n plus 1s by doing the algebra on the right-hand side. Okay, that's how you do mathematical induction. Okay, so I have this first term right here, over 2. What I'm going to do is I'm going to take this one and put it over 2. Okay, I'm going to make it one big fraction, but to do that, to put the 2 on the bottom, I must also multiply the top by 2. So that's what I'm about to do. So I'm going to do 2 n plus 1. That's just some fraction theory right there. I hope that's just finding that common denominator. If I multiply the bottom by 2, got to multiply the top by 2. So now I'm going to distribute both parentheses. No, I'm not either. They both have n plus 1s. I love that. They both have n plus 1s. I need an n plus 1 where that n is. So I'm going to factor out the n plus 1 like a GCF. That would leave me an n plus 2. The n's right here, the 2's right there, all over 2. I'm so close. Okay, remember, what I want to end up with is an n plus 1, where that n is, which I already have, by the way. And then my parentheses, I wanted to say n plus 1, where the n is, plus 1. Well, I can do that. Watch this. I can write that second parentheses like this because 1 plus 1 is 2, which is exactly what was up there. Okay, 1 plus 1 is 2. So I can, look what I did. I replaced that in. I replaced the n up here with n plus 1. I'll replace the n right there with n plus 1. That's all you have to do. As long as what you did is true and you did it correctly, then you're good. One more time. Check the 1, make sure it works. Then get the next term past that n, which is n plus 1. Add it to both sides. Work with the right-hand side until you get the n's right here to become n plus 1s. Once you do that, you've proved it is true for all terms. All right? Hope that makes a little bit of sense. We'll work on it tomorrow. I think you'll start seeing the pattern. Got to be creative sometimes, but that's cool. I'll see you then.